Welcome. This is a special deep dive, and it's crafted just for you, the learner, from the Before AGI podcast.
That's right.
Today, we're jumping into, well, a really fascinating intersection. It's where artificial intelligence meets climate science.
Yeah, it's a huge topic.
And you've told us you want to grasp these complex subjects quickly, but, thoroughly. So that's exactly what we're going to try and do.
Absolutely. Our mission for this deep dive, it's really to unpack how AI is fundamentally shifting our ability to understand and predict the Earth's climate system. It's quite complex. We'll look at the key insights, some really impressive achievements, but also, importantly, the crucial challenges that pop up here.
Right, at the intersection of these two, well, vital fields.
Exactly. We've pulled together some really insightful articles that kind of illuminate this landscape. It's evolving so fast.
So hopefully some aha moments for you without getting bogged down.
That's the plan. No getting lost in the weeds.
Okay, so let's start unpacking this. One of the first big things seems to be how AI is enhancing the climate models we already have.
Precisely. It's not about throwing out the old models, which are, built on decades of physics understanding.
Right.
It's more like, well, giving them a serious boost. AI, especially machine learning, think of it as AI learning from data is just incredibly good at sifting through massive climate data sets.
And finding things we might miss.
Finding complex patterns, yeah. Subtle relationships that maybe traditional statistical methods wouldn't catch easily.
Okay.
And by learning from all that historical data, it leads to something really valuable, more precise forecasts, better projections too.
Including for extreme weather, I imagine. That seems critical.
Definitely. Predicting those extreme events better is a major focus. Machine learning just keeps improving as it sees more examples, sort of like how we learn to recognize, say, storm clouds over time.
That makes a lot of sense. Finding hidden connections. Now, I also read something about making these models much, much faster.
Yeah. Oh, absolutely. That's a huge piece of the puzzle. Think about traditional climate models. Certain parts involve incredibly complex calculations.
Right, they take ages on supercomputers.
Exactly. Huge amounts of computer power, huge amounts of time. What AI emulators can do is essentially learn to mimic those really slow, computationally expensive parts.
Mimic them, but faster.
Much, much faster. There's a great example, Camulator. It managed to speed up a specific component of a climate model, CMA6, by something like 350 times.
Whoa, okay. 350 times. That's not a small improvement.
Not at all. It's genuinely transformative.
So what does that kind of speed actually let scientists do?
Well, it opens the door to running vastly more simulations. You can explore a much, much wider range of what-if scenarios for the climate.
Ah, so testing more possibilities, like different levels of emissions, maybe.
Exactly, or different policy interventions. It's like having the ability to fast forward and rewind potential climate futures much more rapidly.
Okay.
It basically unlocks the potential to tackle research questions that were just, well, too computationally demanding before. You couldn't afford the computer time.
So we get a better handle on the range of possibilities, not just one or two likely outcomes. That sounds incredibly useful for, well, planning anything, really.
Definitely. Now, you mentioned another term earlier, downscaling.
Yeah, downscaling.
Yeah.
What's that all about? It sounds important for local stuff.
It is. It tackles a key limitation of those big global climate models, the GCMs.
Okay.
These GCMs, they operate at a pretty coarse resolution, right? I think grid cells maybe 50 or 100 kilometers across.
So great for the big picture, the whole planet.
Exactly. But not so helpful if you need to know what's happening in, say, your specific city or region.
Right, like using a world map to plan a local bus route doesn't work.
Precisely. So AI comes in, particularly deep learning techniques you might hear about CNNs, convolutional neural networks.
I've heard of those, yeah. Often used for image stuff.
That's right. They're really good at recognizing spatial patterns. So they can learn the complex relationship between the coarse data from the GCMs and finer resolution real-world observations.
Ah, so it learns how to translate the big blurry picture into local detail.
That's a good way to put it. By training on paired data sets, coarse GCM output, and detailed local data, the AI can then perform statistical downscaling.
Taking the global projection and sharpening the focus.
Exactly, down to much finer resolutions, sometimes even 1 kilometer.
1 kilometer, that's incredibly detailed.
It is, and that level of detail is absolute vital for, effective regional planning, designing resilient infrastructure, preparing for local disaster risks.
Because climate impacts aren't uniform, are they? They vary place by place.
Hugely. There was a study in the Eastern Mediterranean, for instance. They used AI techniques, XGBoost and deep learning, I believe, to downscale temperature predictions right down to that 1 kilometer scale. Super valuable for their specific regional challenges.
That kind of local insight must be a game changer for communities trying to adapt.
Okay, so that's models and local detail. What about just regular weather forecasting, like day-to-day stuff?
AI is making massive waves there, too. Really unprecedented accuracy and speed improvements across different timescales.
Okay, like what timescales?
Well, for medium-range forecasts, think predicting the weather several days, maybe up to 2 weeks out.
Yeah.
AI systems, names like GraphCast, Neural GCM, they're actually starting to outperform the traditional physics-based model.
Outperform them. Wow. Those traditional models are incredibly complex, built on physics equations, right?
They are. Decades of development behind them. But these AI models, trained on vast historical weather data, are proving incredibly adept.
That is remarkable. What about really short term? Like predicting rain in the next hour?
That's called nowcasting. And yes, AI models like MetNet are showing amazing results there, especially for precipitation.
Predicting rain showers accurately. Very accurately. And this is particularly valuable in places where you maybe don't have a dense network of ground-based weather radar or sensors.
So AI can kind of fill in the data gaps using maybe satellite imagery or other sources.
Exactly. Leveraging the data we do have more effectively.
And is there more coming down the pipeline?
Oh, yeah. We're seeing the rise of what are called foundation models, something like the Prithvi weather climate model.
Ocean models, trained on absolutely massive data sets.
Enormous data sets covering weather and climate history. And these show incredible promise for potentially handling both short-term weather and longer-term climate applications within a single framework.
Okay, so potentially faster, maybe cheaper, and more accurate predictions across the board.
That's the goal, yeah. The potential is really significant.
This is all sounding incredibly powerful for how we, well, understand and prepare for climate change. So we've got AI boosting the core models, giving us that local detail, revolutionizing weather forecasts. How does this translate into, like, tangible real-world applications? What are we doing with this improved understanding?
Well, a really crucial area is predicting and analyzing those extreme weather events we talked about.
Right. Hurricanes, heat waves.
Exactly. AI can chew through huge data sets, satellite images, sensor data, historical patterns to predict things like hurricane paths and, crucially, their intensity with greater accuracy.
And getting that prediction right and early can literally save lives.
Absolutely. More lead time means better preparation, better evacuation orders. Same idea for heat waves.
How does AI help there?
By spotting subtle precursor patterns in atmospheric data that might indicate an impending heat wave, allowing for earlier warnings, especially for, vulnerable populations.
Okay. What about floods or droughts?
Similar story. For floods, AI analyzes rainfall forecasts, the terrain, how water flows across it, hydrological data to give much more precise predictions of where flooding is likely.
Pinpointing the risk areas better.
Right. And for droughts, it's about analyzing longer-term trends. Precipitation patterns, soil moisture levels, how much water is evaporating. AI can integrate all that to provide earlier and more reliable drought warnings.
So right across the spectrum of these damaging extreme events, AI is sharpening our foresight.
It really is, giving us a clearer picture and hopefully more time to react and adapt. There are even advanced machine learning techniques, things like autoencoders.
What do I do?
They're good at learning what's normal in data, so they can then flag things that are unusual or anomalous. This helps detect maybe rare, intense rainfall events or strange climate patterns that could be linked to extremes.
Finding the needles in the haystack, basically.
Sort of, yeah.
Right.
Identifying critical signals.
Okay, so beyond just predicting the weather and climate itself, is AI playing a role in how we manage things like our energy systems, especially with renewables coming online?
Oh, definitely. That's another huge application area. Integrating renewables like wind and solar isn't always straightforward, right? Their output fluctuates.
Yeah, it depends on the weather.
But
Sunny, windy, or not.
exactly. So AI is fantastic at analyzing weather forecasts alongside electricity demand patterns. It can predict, much more accurately, how much power those wind farms or solar panels are likely to generate.
Helping grid operators know what to expect, balancing supply and demand.
Precisely. It helps them anticipate surpluses or shortfalls, making the grid much more stable and efficient.
That must make managing the grid way less of a guessing game.
It does. And AI doesn't just predict the generation, it also optimizes how we use energy storage, like big batteries. By forecasting future demand and renewable supply, AI algorithms can figure out the smartest times to charge those batteries, maybe when there's excess solar power and when to discharge them to support the grid, like during peak evening demand.
So making the most of the clean energy we generate and reducing reliance on, say, fossil fuel backup plans.
That's the idea. Makes the grid cleaner and more robust. And speaking of robust, AI is also enhancing grid resilience itself.
How? By
Uh-huh.
predicting problems.
Yeah, by analyzing real-time data from sensors all over the grid, it can spot potential vulnerabilities, maybe predict when equipment needs maintenance before it fails.
Preventing blackouts?
Helping to prevent them, yes. And if an outage does happen, AI can help analyze the situation and assist in rerouting power to restore it faster.
Okay, so AI is not just helping us understand the climate problem, it's actively helping us build infrastructure that's more resilient to it. That feels really important.
It's a powerful combination, absolutely.
What about monitoring the environment more broadly, beyond just weather and climate models?
This is another area where AI shines. Think about the sheer volume of data coming from satellites constantly imaging the Earth, plus ground sensors.
It's overwhelming, I bet.
It can be for traditional analysis, but AI is brilliant at processing this flood of information. It can track really critical environmental indicators in near real time.
Like what kind of indicators?
Things like deforestation rates. AI algorithms can analyze satellite images month after month and automatically detect where forests are being cleared much faster and often more accurately than manual methods.
Wow, and ice melt, that's a big one.
Huge. AI rapidly measures changes in the extent and even the volume of ice sheets and glaciers in Greenland, Antarctica, mountain ranges. It can also monitor things like sea ice extent.
Providing a constant checkup on these critical planetary systems.
Exactly. Water quality, too. Analyzing spectral data from satellites or sensors to monitor algae blooms or sediment levels in lakes and coastal waters.
It's like having this, I don't know, AI-powered planetary health dashboard.
That's a pretty good analogy, yeah. It can even spot subtle things, detecting the appearance of small meltwater ponds on Arctic ice, or tracking the thaw of permafrost, which releases greenhouse gases. Things that are hard to monitor consistently over vast areas otherwise.
And getting that detailed, near real-time environmental data must then feed back into improving the climate models themselves, right? It's a loop.
Absolutely. It's a virtuous cycle. Better observations lead to better model tuning and validation. This detailed monitoring helps us refine our predictions of climate change impacts.
And get more specific about where and when those impacts will hit hardest.
Precisely. Refining projections at those finer spatial and temporal scales we discussed. Getting a much clearer, more localized picture of how things like average temperatures or rainfall patterns are likely to shift over the coming decades.
And does it help with exploring different futures too? Like under different emission scenarios?
Yes, AI can significantly speed up the process of generating those climate projections, running the models under various assumptions about future greenhouse gas emissions to understand the long-term consequences of the choices we make or fail to make today.
It really is touching almost every aspect of climate science and response, isn't it?
It's becoming deeply integrated, yeah.
So this all sounds incredibly promising, but are there challenges, hurdles we need to overcome?
Oh, definitely. It's not all smooth sailing. One of the big ones often talked about is the black box problem.
Meaning we don't always understand how the AI reaches its conclusions.
Exactly. Especially with complex, deep learning models. They can be incredibly accurate, but their internal workings, the chain of reasoning, can be very opaque.
And that's a problem for science, right? We need to understand the why.
It is. It hinders trust, makes it harder to diagnose errors, and limits the scientific insights we can gain from the model beyond just the prediction itself.
So what's being done about that? Is there a solution?
There's a whole field called explainable AI, or XAI, that's focused specifically on this.
Yeah, okay.
XAI techniques aim to make these models more transparent. Things like visualizing which parts of the input data the model focused on, identifying the key features driving a prediction, or even designing AI architectures that are inherently more interpretable.
So trying to open up the black box.
Essentially, yes. Enhancing interpretability builds trust and helps scientists refine the models further.
Makes sense. What other challenges are there? Data, maybe? AI needs lots of data, doesn't it?
Huge amounts, and not just quantity, but quality. Training effective AI climate models requires vast data sets that are accurate, well-labeled, and standardized.
Is getting that data a bottleneck?
It can be. There are efforts to create large benchmark datasets specifically for this purpose, like ClimateSet, which helps researchers develop and compare machine learning approaches for climate modeling. But data availability, quality, and access can still be hurdles.
And what about the computing power needed? We talked about speed-ups, but training these big AI models must still require a lot of grunt, right?
It does. Complex AI models, especially foundation models, demand substantial computational resources, huge clusters of GPUs, massive energy consumption.
Right.
While emulators like Camulator show we can gain efficiency in using models, the initial training is still very resource-intensive.
Which leads to another point I saw mentioned, the environmental paradox.
Ah, yes. The irony that the very tool we're using to fight climate change AI has its own significant carbon footprint.
From all the energy needed for data centers and training these massive models.
Exactly. The International Energy Agency, the IEA, projects that electricity consumption from data centers, AI, and cryptocurrencies could potentially double by 2026 compared to 2022 levels.
Wow, that's concerning.
It is. It highlights the urgent need for developing more energy-efficient AI algorithms, hardware, and focusing on sustainable computing practices. We need to ensure the cure isn't contributing significantly to the disease, so to speak.
A really crucial point. Are there ethical considerations too, beyond the energy use?
Absolutely. Like any powerful technology, AI in climate science raises ethical questions. One is bias.
Bias, how?
AI models learn from historical data. If that data reflects existing societal biases or inequalities, maybe sensor networks are denser in wealthy areas, or historical impacts disproportionately affected certain communities, the AI can learn and even amplify those biases.
Leading to unfair or inequitable predictions or resource allocation.
Potentially, yes. So ensuring fairness, transparency, and accountability in how these AI systems are developed and deployed is critical. We need to be really careful about who benefits and who might be left behind or even harmed.
Lots to think about there. So looking ahead then, considering all these advancements and challenges, what does the future landscape look like? Is it AI completely taking over or something else?
I think the consensus is moving towards a synergistic future. It's likely not AI replacing traditional physics-based models entirely.
But working with them.
Exactly, combining the strengths of both. You leverage the deep physical understanding and consistency built into the traditional models, but you enhance them with AI's efficiency, its pattern recognition prowess, and its ability to handle vast data.
A hybrid approach.
Precisely. We're already seeing this. AI improving specific, complex parts of traditional models, parameterizations they're called, or AI emulating certain components like we discussed with Camulator, or even AI helping scientists make sense of the massive outputs from the traditional models.
So the future is probably about smarter integration, leveraging the best of both worlds.
That seems to be the most promising path forward. Physics-informed AI, AI-accelerated simulations. Bringing these two powerful approaches together holds immense potential for pushing the frontiers of climate science.
Okay, right. Let's just unpack what this all means for you, the learner, especially tuning in from the Before AGI podcast perspective. You should now have a much clearer picture of how deeply AI is getting woven into our efforts to understand and predict climate change. From making forecasts faster and more accurate to uncovering these crucial insights about how our environment is shifting, sometimes in subtle ways. AI is really proving itself to be a powerful ally here.
A critical tool in the toolbox.
Definitely. And here's where it gets, I think, really interesting for anyone following AI. The sheer speed of innovation, it's just incredible. It means we're constantly pushing the boundaries of what we thought was possible in using AI for climate solutions.
The progress, even in the last few years, has been remarkable.
Which kind of raises a big question for you to think about. As AI becomes ever more integrated into climate science, how do we make sure its development and, crucially, its application are both effective and ethically sound?
That's the key tension, isn't it?
Yeah, finding that balance between the immense power of these AI tools and the profound responsibility we have in using them wisely and fairly. Something to really mull over.
And if we connect this back to the bigger picture, the themes we explore on the Before AGI podcast, this deep dive really showcases the potential, right? The potential of these increasingly intelligent systems to help us tackle some of humanity's absolute greatest challenges.
Yeah.
Climate change is arguably at the top of that list. So this is really a glimpse into a future where AI could be, truly instrumental in helping us build a more sustainable world. It's not science fiction, it's happening now.
Absolutely. For more explorations just like this one, looking into the world of AI and its transformative potential, make sure you are subscribed to the Before AGI podcast.
Mm-hmm.
And for those of you who want to get your hands dirty, maybe dive even deeper with tutorials and more insights into actually building and using AI, you should definitely check out my YouTube channel. It's Ian Ochieng AI. That's Ochieng AI.
Great stuff on there.
Thanks so much for joining us on this deep dive.